All right, it has been a while, but there's like one more topic that I haven't really covered that is pretty freaking important, so I'm going to cover it. And it's basically most of thermo. So I'm going to do it in a couple of videos. So this first video is going to be on energy balances, and the next video will probably be entropy balances. And then the last video will be compressors and turbines. I think that's how it's gonna go. So this first, well, okay. Also a disclaimer, I haven't used these, I haven't done math on these equations in a while. At least complex math. I've done basic math, but so I might get a couple things wrong, but hopefully not. So whenever someone says they're doing a thermodynamic energy balance, what equation do they start out with? This is the equation. So the total energy equals the internal energy, that's a U, it's a capital U, plus the kinetic energy, plus the potential energy, which also equals the heat added to the system minus the work done by the system. The signage of these two terms confuses a lot of people, and you can kind of use whatever signage you want as long as you know what you're doing. But as I mentioned, the way it's written here is a positive Q is heat being added to your system, and a positive work is work that your system does. So one's in and one's out, so it's backwards, but that's how it's written, so I'm going to write it that way here. Okay, plus M, do I write J? I'm going to write J and just, yeah, okay. Minus MJ out. Okay. Really quickly, I want to get rid of these J's because I've never used them ever. Technically, well, okay. So this whole term represents the total energy coming in to your system, and this whole term represents the total energy leaving your system in terms of like mass. These are also energies, but there's no like mass entering or exiting. And the mass, it could be, let's say you're adding really cold air to a box. The box, or to like a bottle or something, the bottle won't heat up. But if you add really hot air to the bottle will heat up. That sounds very dumb, but the idea is this is half v squared, and if you multiply in the m, it's mv squared, so that is the same thing that's over here, 1/2 mv squared, plus g, I would call it h, but I'm not going to because h is enthalpy, z for height, and that's the same thing that's over here, mgz, plus h, which is enthalpy. But on the left side, we have U, which is internal energy. So what is the difference? Well, it's capital U. So let me finish writing down the equations and then we'll get, well, okay. So typically this stuff cancels out. You don't care about it, but I'll leave it here for now and we'll see that it usually cancels out anyways. Okay, so U over here, U equals, because it's a capital U, you multiply it in the mass. So it would be mCv times temperature. And the h on the right here, since it's a lowercase, since the mass is outside of the J, it would just be Cp times temperature. So Cp versus Cv. Okay. I'm going to do some example problems for this all to make sense, but there's one more equation. W. So this could either be pressure times a change in volume, or force times a change in distance. One of those two. Kind of, you just use whichever one's easier for the problem. So let's do, I had two examples written out. Maybe I'll think of a third one by the time this is done. So, yes, the pipe one. So let's say you have a pipe. That's a freaking long pipe. So you have a pipe, and let's say there's air coming in one side and leaving the other side. Cool, and it's entering at a T1, P1, and it's leaving at a T2, P2. Let's assume you know T1, you know P1, and you know P2, and you're asked to solve for T2. But there's a frickin' twist. Heat is being added to the system. Let's say the pipes are heated, which is actually a thing that happens in the real world. I've worked with pipes that have been heated before. Cool, so let's say it's heated and you're asked to calculate the final temperature. So what would you do? How would you use this energy balance equation to solve for that? Well, okay, so you can cross out U because there's no internal energy, because there's internal energy if there's a box and the stuff inside of it gets heated up, and but the stuff inside of it stays there. In this case, the stuff inside doesn't stay because it just goes out, goes in one side, goes out the other side. So U cancels out. Ke, let's assume V1 equals V2, which if you're in a thermo class, you can probably always assume that because they don't want you to waste your time doing physics. They want you to do thermo. And then the height cancels out also because let's assume the average height is the same on both sides. Average height of the mass of the air. Okay, so we have a Q. W. Do we have a W? We do not have a W because nothing's really moving. No boundaries are moving. If this top boundary was like slowly moving up, then we would have work and this problem would be more complicated. But fortunately, that is not the case. Okay, and then MJs. So we do have, well, okay. We assumed that the V's were the same, so that cancels out. We assumed the heights were the same, so that cancels out. We are left with H's though. And the reason for that, well, as I mentioned, everything in the system is moving. It's going in and going out. Nothing's staying in the system. So if something's going in or going out, we use H. If something is in the system and stays there, then we use U. And the only difference is U is CV and H is CP. Okay, so our final energy balance equation, 0 equals Q plus M. I'll factor out the M. And then we have H in minus H out. Cool, and then if you are using a program like Ease or literally just any online thermodynamics tool, you can solve for this because you know Q, let's assume you know M also, and H is a function of T and P, and you know both of those, and you also, well, in this case, you know P2, but you don't know T2, and you can solve for T2 that way. Cool. I know I kind of sped through that, and I'm not going to do numbers, partially because I don't want to mess up, and partially because I don't want to use numbers. But there you go. That is problem 1. So problem 2, let's say this is a classic problem. Very straight lines, I like it. Let's say there is like a cylinder. Let's say this thing is a freaking cylinder. And there's a round disc that's floating in the cylinder. And it's like it's not a friction fit, but it's like just tight enough where the air underneath it, so let's say this is air, where the air underneath it can't escape through the sides. So like this is like right next to the wall. Cool. And you're adding heat to the system. How would you use the energy balance? Well, okay, first of all, what would happen? As you heat up the air, I mean, you have, what is it? PV equals nRT. If you heat up the air, the temperature goes up. N stays the same. R stays the same because it's air. Well, N stays the same because no mass is entering or leaving, so the number of moles of air stays the same. Pressure would stay the same because this, let's say this disk has a set mass. And if this disk moves higher up, it's still going to have the same mass. So, and pressure is weight over area in this case, I think. And it has the same weight because it has the same mass, and it has the same area because the disk is the same size as it was lower down. So pressure stays the same. So if temperature goes up, volume has to go up. So what should happen is the disk gets moved up by a certain distance. We'll call it x. Conveniently, we'll call it x. We'll use this version of work. Okay, so let's rewrite the energy balance. U equal, nope, got it wrong already. Q minus W plus MJ minus out. Okay. So we have a Q, we have a work, and for the work, we're going to use force times change in distance. We have a U because in this case, all the air is still staying in here. None of it's like being fed in and leaving. Well, or none of it's just being fed in, because if more air was being fed in, it would push up the piston even more. And if more air was being taken out, it would lower the piston. So maybe we could spin this off and I could prove that later on. But okay, so we have U. Kinetic energy, 0, because the air in here, technically, it's not moving. It is moving as the piston goes up, but let's assume we're at state 1 where the piston is right here, and state 2 where the piston is right there. And everything stopped. So V equals 0. PE, technically the center of gravity of the air in state 1 is probably here, and at state 2 is probably there. So there is a slight change in height. But I'm going to assume that that is negligible, which you can pretty often assume in thermodynamics. Because like I mentioned, they want you to do thermodynamics and not physics 1. Water. Yum. Okay. You have Q, you have W because you have force X. All right, MJ. You don't have any MJs because there is nothing entering or leaving. There's no mass entering or leaving the system. No mass of air entering or leaving. Okay, so let's write this out as a function of state 1 and state 2. So U, we could do M of air, U1 minus U2. Is that it, or do I do U2 minus U1? I think I do 2 minus 1, actually. I could figure that out on my own, but I just looked at my equation sheet. Okay, so you have 2 minus 1 equals Q, which we'll assume is a fixed amount of heat. Like, let's say it's 10 joules. I don't know, some number like that. Minus the work, which is force times X. And the force is the mass of the piston, which is this thing, times gravity. So that's the force, and times X. Let's just call it X. Times this height. And that is it. So, U, what is that? What is U? CV delta T. So this becomes, you could even take out the CV. CV T2 minus T1 equals the rest of it. Cool. So if you add heat and you know the starting and final temperatures, you can say how much the piston went up. Very cool. And then if you, so I mentioned before, if you add air to the system, like let's say right there, there's a pipe and you're adding air into the system. You would also add MJ, which like always boils down to MH. And if this is a positive number, X should increase because there's a negative sign out front, which makes sense. It's like blowing up a balloon. If you're blowing air into here, it will push the piston up more. So that sanity checks out. But let's say you are removing air. Let's say the weight of the piston is pushing down on the air and pushing it out. This would be a negative. And that goes down. This would also have to go down to balance out. Cool beans. Okay. I think that's pretty much it for energy balance. So again, this is the big equation. Yeah, and these are all the terms written out. You have internal energy, which is if you have stuff in your system that's just sitting there. And it's sitting there at the start and at the end, at state 1 and state 2. And you have velocity, the kinetic energy velocity term, and that's all, like, you can almost always cancel that out. Same with potential energy. Q is heat added or removed from the system. Work is pressure times delta volume, or force times delta x. J is v squared, height, and h. And you use h when stuff is flowing in or out of the system, not when stuff is sitting in the system. Cool beans. All right, I was a bit hesitant when writing my answer for this because I was like, well, okay, let's simplify it back down to just the starting problem. Yeah, there you go. Okay, so I was a bit hesitant in writing this out because I'm like, dang, you need to know Q, T1, T2, mass of air, massive piston, and then you can calculate X. And I'm like, you basically need to know everything. And that's a very easy problem at that point. I'm like, surely there's a way to do it without having to know all of that stuff. And I think there is. And I think the way to do it is you have, I might have even talked about it down here or over here at some point. I don't know. All right, so you have PV equals nRT. N doesn't change because no air is entering or leaving the system, so the total number of moles of air in the system is the same. R is the same because it's air. If it somehow switched to a different thing, then R would change, but in this case it doesn't. P is the same because the pressure is set by the weight of the floating piston, and the floating piston is the same weight as state 1 and state 2. So now you can relate V and T. So the way to do that would be P1 V1 over N1 R1 T1. So I just divided all this stuff onto the denominator. Equals P2 V2 over N2 R2 T2. Cool, and we said P1, P2 are the same, N1, N2, R1, R2. So we're left with V1 over T1 equals V2 over T2. Cool. So now we need one less variable. And how does this help? So the temperatures, they're right there. Where are the volumes though? So the volumes are in X. So X technically equals volume, well, okay. What would it be? Volume 1 is, what shape should I have it be? Let's have it be a cylinder, which I think I did have it as a cylinder before. It would be pi r squared h1 v2 equals pi r squared h2. Pi r squared stays the same because radially it's not changing. X is h2 minus h1. So it is H2 is V2 over pi r squared minus V1 over pi r squared. So that is what x equals. And now we have V's up here, V's up there, and we have V's down here. So now we need one less variable. And I think that's the most amount of simplification you could do for this problem. Because now we have two equations and two unknowns. And I think that's it.